Some brain regions can take short naps while the rest of the brain is active. Different parts of our brain take short naps while the rest of the brain is active, according to a new study. It turns out that parts of our brain can sleep even when we are wide awake. New research in mice suggests that there are patterns of brain activity related to sleep that we have missed and that reflect the state of individual brain regions, not the entire brain. By measuring these local signals with electrodes, scientists have found that some regions of the mammalian brain can take short naps while other areas remain fully awake and active. The results in a description of the study were published in the journal Nature Neuroscience. Sleep and wakefulness are two basic physiological states that occur cyclically. About a third of the day is spent asleep, the rest is spent awake. These two completely separate states define the boundaries of our daily lives. For years, scientists have measured the difference between these processes by recording and analyzing brain waves. During wakefulness, alpha and beta waves occur. During sleep, the faster alpha and beta waves disappear and the slower theta and delta waves appear. In a new study, scientists have discovered that sleep can be detected from patterns of neural activity lasting just milliseconds, or 1,000 times less than a second, revealing a new way to study and understand basic brainwave patterns. They also showed that some areas of the brain can temporarily exhibit sleep patterns while awake, and vice versa. The findings were made possible by artificial intelligence. The researchers spent more than 4 years training a neural network to learn to analyze brainwave patterns. In their experiments, they equipped mice with small, lightweight sets that recorded brain activity from 10 different areas. For a month, they tracked brain waves from small groups of neurons with microsecond precision. In the process, they generated several petabytes of data. The team of scientists fed this huge amount of data to the neural network, which eventually learned to find highly complex patterns about sleep and wakefulness that humans would have no chance of seeing. The researchers found patterns at high frequencies that had never been described before. The researchers fed small pieces of data into the neural network and asked whether the brain was asleep or awake. Their neural network learned to distinguish between sleep and wakefulness based on just milliseconds of brain activity data. This surprised the research team. It showed that the model couldn't rely on slow waves to learn the difference between sleep and wakefulness. Just as listening to a song for just 1,000th of a second can't tell us whether it has a slow beat or not. We're seeing information at a level of detail we've never seen before, said David Haussler of the University of California, Santa Cruz. We initially thought we wouldn't find anything there, that all the important information was in the slower waves. But it turns out that if you ignore the conventional measurements and just look at the high-frequency detail over just 1,000th of a second, there's enough there to tell whether the brain is asleep or awake. That tells us that something is happening there on a very fast scale. This is a new clue to what might be happening during sleep, he added. An artificial neural network is essentially a black box, and it doesn't report what it learns. Scientists began stripping away layers of temporal and spatial information from the data to try to understand what patterns the model was learning. Eventually, they got to the point where they were looking at fragments of data that were just a millisecond long and recorded at the highest frequencies. We stripped away all the information that neuroscience has used to understand, define, and analyze sleep for the last century and asked ourselves, can the model still learn under these conditions? That allowed us to look at signals that we didn't understand before, said David Parks of the University of California, Santa Cruz. The researchers eventually determined that these rapid patterns of activity between just a few neurons were the fundamental element of sleep that the model was detecting. Importantly, such patterns could not be explained by traditional slow waves. The researchers hypothesized that slower waves might act to coordinate fast, local patterns of activity, but ultimately concluded that fast patterns are much closer to the true essence of sleep. If the slower waves traditionally used to define sleep are compared to thousands of people in a stadium doing a Mexican wave, then these fast-moving patterns are conversations between just a few people deciding to participate in the wave. These conversations are essential to its occurrence, and are more directly related to the mood of the stadium. As the researchers further studied the local activity patterns, they noticed another surprising phenomenon. When they observed the model predicting sleep or wakefulness, they noticed what at first glance looked like errors, in which for a fraction of a second the model detected wakefulness in one brain region while the rest of the brain remained asleep. They observed the same thing in wakefulness. For a fraction of a second, one brain region fell asleep while the rest of the brain was awake. The researchers called this a flicker. We can look at the individual time points at which these neurons fired, and it's pretty clear that they're switching to a different state, said Aidan Schneider of Washington University in St. Louis. In some cases, these flickers may be limited to just one brain region, he added. That led the researchers to investigate what the flickers might mean for sleep function and how they affect sleep and wakefulness behavior. A small part of the brain goes to sleep when you're awake, so does that mean that your behavior suddenly looks like you're asleep? We started to notice that this was often the case, Schneider said. By observing the behavior of mice, the researchers noticed that when one region of the brain goes to sleep while the rest of the brain is awake, the mouse pauses for a moment, as if it freezes. On the other hand, when one region of the brain is awake while the rest is asleep, the mice exhibited body tremors during sleep. Gaining a deeper understanding of sleep patterns and flicker could help scientists better study neurodevelopmental and neurodegenerative diseases that are associated with sleep deregulation. The researchers want to continue their research, including using brain organoids, tiny versions of different organs grown in the lab that retain key anatomical features of full-size organs to help them do so.
Pas de soleil, 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 pas de soleil.